So let's
All right,
finish up the lecture on acid base with what is the pH of a 0.4 molar ammonia solution. Well, to do this, we need to know the Kb. And the Kb for ammonia is 1.8 times 10 to the minus fifth. Okay? Again, not something you have to memorize, something that would be provided in a table. And so we're going to attack this problem just as if we were doing an acid problem. Okay? We're going to determine what are the major species in solution. Okay? So ammonia, the initial concentration of that is 0.4 molar. When that reacts with water, we form the ammonium ion and the hydroxide ion. So the hydroxide ion, the ammonium ion, and ammonia are the major species at equilibrium. We're going to ignore the autoionization of water. Okay? So then we set up our ice table. Initial change equilibrium. Our initial concentration of ammonia is 0.4 molar. The ammonium ion is 0. The hydroxide ion is 0. We lose X ammonia and we gain X in both ammonium and hydroxide. And at equilibrium, it's 0.40 minus X and X and X. Now, because this is a weak base, we can also try our approximation that we talked about for acids. So, insert our values into Kb expression. We get X squared is 0.4 minus X. But since 0.4 minus X should be approximately 0.4, that gives us our Kb equals X squared over 0.4, which yields X being 2.7 times 10 to the minus 3. We check to see if that is a valid approximation. So, when we determine the percent dissociation, that is 0.68. That is a valid approximation. Therefore, at equilibrium, the hydroxide ion concentration is 2.7 times 10 to the minus 3. And the pOH is 2.57, negative log of the OH concentration. So the pH is 11.43. The pH, note that the pH is basic, which would make sense because ammonia is a base. So how are Ka and Kb related? Well, if you write out the Ka expression and the Kb expression, when you add the two up, you get Kw, which means that Ka times Kb equals Kw. So if you know the Ka, you can find the Kb of its conjugate base by taking Kw over Ka, or if you know the Kb, you can find the Ka of the conjugate acid by taking Kw over Kb. Now, this is important because a lot of times we only give you Ka values, and you have to determine the Kb value from the Ka value and vice versa. Now, for diprotic and triprotic acids, this is going to be a stepwise loss of protons. So H2SO4 is a strong acid, but only the first proton coming off. So H plus plus HSO4 minus. The HSO4 minus, when that loses a proton, that is a weak acid. So we actually have an ionization constant expression for each different ionization stages. Okay? Which means that we have to use all of those equilibrium calculations in order to determine if we have, or to determine what concentration of H plus we have. So from this, we can see that sulfuric acid, the Ka is very large, but hydrogen sulfate is 1.3 times 10 to the minus 2. Now, this means that when you put sulfuric acid in water, most of the concentration is going to come from our first proton coming off. Okay? But there is a fairly significant amount of secondary proton coming off. So let's do a diprotic example. Oxalic acid is a poisonous substance used chiefly as a bleaching and cleansing agent, for example, to remove bathtub rings. Calculate the concentrations of all the species present at equilibrium in a 0.1 molar solution. All right, so we're going to have to do this in a stepwise note, okay? So each time we do an ionization, we have to determine the concentrations. So, the major species in the first step is we've got our oxalic acid, hydrogen ion, and hydrogen oxalate ion. So we start off with 0.1, 0, and 0. We lose x, gain x, gain x. Always set up your ice tables. 0.1 minus x, x, and x. If we use our approximation, 0.1 minus x is 0.1, then we've got this situation here, where Ka is equal to x squared over 0.1, and we get a concentration of x as 8.1 times 10 to the minus 2. Now we need to determine, is that a valid approximation? And since that is 81%, it's not a valid approximation. So we have to do the quadratic. When you solve the quadratic, this is what you get. Okay? And the result is 0.054 molar. I'm not going to go through and solve the quadratic. You guys can do that on your own. So the first stage of ionization leaves us with this: 0.054 molar H plus, 0.054 molar in HC2O4 minus, and 0.1 minus 0.054 or 0.046 molar in terms of oxalic acid. So that's the first ionization. The second ionization, we're going to take the HC2O4 minus and deprotonate that. So we start off with 0.054, 0.054, and 0. This is the key part, is we're starting with an ion here in this position already. Don't forget that you've already calculated out that H plus ion concentration from the first ionization. Subtracting y, adding y, 0.054 minus y, 0.054 plus y, and y. Okay? Now, the Ka for the hydrogen oxalate ion is 6.1 times 10 to the minus 5. So when I put this into my equation, I get 0.054 plus y times y over 0.054 minus y. Now, we can still do our approximation. Following the approximation, the 0.054 plus y is still 0.054, and 0.054 minus y is 0.054, which gives us 0.054 y over 0.054, which is equal to y, which is equal to 6.1 times 10 to the minus 5. Test the approximation, this time using the concentration of the HC2O4 minus ion. So 6.1 times 10 to the minus 5 over 0.054 gives us a 0.11, so the approximation is valid. So then, at equilibrium, we have our oxalic acid concentration that we found in the first step. We have our hydrogen oxalate concentration, which we found in the first step. The H plus ion concentration is 0.054 plus the 6.1 times 10 to the minus 5, or 0.054 molar. And C2O4, 2 minus, is 6.1 times 10 to the minus 5th. And this time, they ask for all ions. Since they ask for all ions in solution, we also have to include the hydroxide ion, which we find from Kw over H plus ion concentration, and we get that as 1.9 times 10 to the minus 13th molar. Molecular structure also impacts acid strength. So the stronger the bond between the hydrogen and whatever counter ion is there, the weaker the acid. Okay? So in terms of our mineral acids, HF, HCl, HBr, HI, HF has a much stronger bond. So the concentration, sorry, not the concentration, but the ionization of HF is much smaller than it is for HCl, which is smaller than it is for HBr, which is smaller than it is for HI. So out of all of those acids, HI is the strongest of the acids. And this is borne out by looking at the bond enthalpies. The bond enthalpy for HF is 568.2. That's a weak acid. 431, 366, 298.3. 298.3 for HI, that is the strongest of the acids. Now, it turns out that if you have salts, can have acid and base properties as well. So you can have neutral solutions from salts, or you can have acidic solutions from salts, or you can have basic solutions from salts. To get a neutral salt solution, this is going to be an alkali or an alkaline earth metal, except for beryllium, and the conjugate base of a strong acid. Strong acid. So sodium chloride, you can think of as being the reaction of sodium hydroxide plus hydrochloric acid. Strong base, strong acid. So neutral solutions come from strong bases and strong acids. Remember, the conjugates of those strong things are weak. Now, if you have a strong base and a weak acid, the solution will be basic because, so for example, acetic sodium acetate, you can think of as NaOH plus HC2H3O2. This is a weak acid, which means the conjugate base, C2H3O2 minus, is strong. Okay? So that's a stronger conjugate base, therefore the solution will be basic. To get an acidic solution, you'd have a strong acid and a weak base. Okay, so something like NH3 plus HCl. That's going to form NH4Cl. So ammonium chloride is going to be an acidic salt solution. Okay, because the ammonium ion is a stronger conjugate base, or sorry, stronger conjugate acid. Okay. We can calculate the pH of a salt solution using Kas and Kbs for our conjugate acids and bases. So calculate the pH of a 0.15 molar solution of sodium acetate. What is the percent hydrolysis? So first thing, sodium acetate. Okay, we would expect sodium acetate is going to be strong base, weak acid. So we would expect the base, the salt, to be basic. Okay? So, what we do is we set up our ice table. Okay? Now, since this is a soluble salt, the ice table is actually pretty simple. We start off with 0.15 molar sodium acetate, 0 and 0. When it all dissolves, we don't have any more sodium acetate. It's all been dissolved into sodium and acetate. So the initial concentration of 0.15 is now a final concentration of 0. And the initial concentrations of 0 are now initial concentrations of 0.15. Now, this reacts with water. Okay? The acetate ion reacts with water to form acetic acid and hydroxide ion. That is why this is a basic salt. So now we take 0.15 molar, 0, 0, minus x, plus x, plus x, 0.15 minus x, x, and x. And now we need to know what is the Kb for acetate. We look that up in the table. We get 5.6 times 10 to the minus 10th equals x squared over 0.15 minus x. Now, we're going to solve this using the approximation, and I'm going to tell you, whenever you have a very small Ka or Kb and a fairly large concentration, your approximation is almost always going to hold. Okay? It's when you have a large Ka or large Kb and even a large enough concentration that the approximation doesn't hold. So when we do the approximation, we get 9.2 times 10 to the minus 6th molar. Putting that in to pOH, we get 5.04 as the pOH, or the pH is 8.96. Now, the percent hydrolysis is the same as our percent ionization. This is what we would use to determine whether our approximation was valid or not. And the approximation is valid at 0.0061%. And this slide just says exactly what I just said. Solutions derived from a strong acid and a weak base. We've already gone through this. NH4Cl, when it dissolves in water, gives us ammonium ions and chloride ions. The ammonium ion is a stronger conjugate acid. So, solutions in which both the cation and the anion hydrolyze. Okay? So, this is, what if you've got weak acid, weak base. Okay? If the Kb for the anion is greater than the Ka for the cation, the solution will be basic. If the Kb for the anion is less than the Ka for the cation, the solution is acidic. And if the Kb and the Ka for the cation and the anion are similar, the solution will be close to neutral. Okay? So you have to know your Kas and Kb values in order to determine whether your solution is going to be acidic or basic or neutral if you have weak acid, weak bases. So here is a simple little acid-base properties of salts. You can see all of our strong acid, strong base, no ions that undergo hydrolysis. pH is around 7. Okay, you got a strong base, weak acid, pHs are greater than 7. Weak base, strong acid, pH is less than 7. And then anion and cation, it's around 7, less than 7, greater than 7, depending upon the Kb. Okay? Now, small highly charged cations and an anion from a strong acid. These are always going to be less than 7. Okay? And we'll talk about why that is in just a minute or two. Okay. So let's predict whether the solutions will be acid, basic, or nearly neutral. So ammonium iodide. That is a strong acid, weak base. So the NH4 plus is going to be a stronger conjugate acid. So the solution is going to be acidic. Sodium nitrate. That's sodium hydroxide, which is a strong base, plus nitrous acid, which is a weak acid. So the NO2 minus ion is going to be a stronger conjugate base. Therefore, the solution is going to be basic. FeOH taken 3 times plus HCl is a way you can think of this. This is not a strong base. It's a weak base with a strong acid. So the iron 3 plus ion is going to be a stronger conjugate acid. So the solution is going to be acidic. Now for NH4F, we need to know what are the Kas and Kbs for HF and NH3. NH3 is 1.8 times 10 to the minus 5. I don't know what HF is, but I'm pretty sure that they'll tell us in the problem here. So the Ka for ammonia, for ammonium ion, is 5.6 times 10 to the minus 10th, and the Kb for the anion is F minus, is 1.4 times 10 to the minus 11. So this is greater than the Kb. Ka is greater than Kb. The solution will be acidic. Not very acidic, but slightly acidic. All right, acid definitions. Just a recap. Arrhenius acids are substances that produce hydroxide ions in water. Arrhenius bases produce hydroxide. I said that backwards. Arrhenius acids are substances that produce hydronium ions in water. An Arrhenius base produces hydroxide ions in water. A Bronsted-Lowry acid is a proton donor. A Bronsted-Lowry base is a proton acceptor. There is a third one we're going to talk about, and that is Lewis acid-base theory. Lewis acids are substances that can accept a pair of electrons. So they're an electron pair acceptor. And a Lewis base is an electron pair donor. So Arrhenius acids and Bronsted acids are essentially the same thing, but a Lewis acid is completely different. Now, you can think of a Lewis acid as something that is electron deficient, and a Lewis base is something that is electron rich. So electron deficient and electron rich. Nothing is more electron deficient than a proton without an electron. So that is definitely an acid. Nothing is more rich than a hydroxide ion with 3 pairs of electrons that it can donate to something else. Okay? So this is why Fe3+, it is electron poor. It is a Lewis acid. Okay? That's what we saw in the last problem. Now what this does is this really opens up what an acid or base can be, because there's not any need for proton donation. Okay? BF3 can react with ammonia to form an ammonium boron trifluoride adduct where no protons are donated or accepted. This is an acid-base reaction. You're going to see in organic chemistry that a lot of acid-base reactions occur in this fashion. And you can read all about stomach acid and different things to neutralize it.